So in the last video, I introduced this idea of physiological cross-sectional area as being the cross-sectional area of the muscle fibers in the direction of the muscle fibers themselves. So I've got two examples of muscles here, one of which a fusiform muscle where more or less the muscle fibers are in the same direction as the tendon itself. This might be maybe the long head of the bicep over here. Whereas over here, maybe your medial gastroc has muscle fibers, which remember those are made up of stacked together myofibrils, which are in turn made up of sarcomeres in series. They are headed off like this. Now, what's different about these two? The way you would measure, say, with an MRI, if you did an MRI and you took a cross-sectional slice of the muscle and you found its area, which is something you can do in an MRI, that would give you something that we call the anatomical cross-sectional area. Same thing as if you got some like a measuring tape and you measured the circumference of a muscle and assumed it was a circle and tried to find its area. That would give you the anatomical cross-sectional area. That's different than the physiological cross-sectional area in cases where you have the muscle fibers going off at a different angle. And the name for that different angle, remember, is that pennation angle. Now, most muscles have a pennation angle that's relatively small. The largest ones that I know of in the lower body are maybe on the order of 20 degrees. So it's not really drastic. And in many cases, like for example, the muscles of the quadriceps are maybe a good example of this. In many cases, it's very close to 0 degrees, and so the anatomical cross-sectional area is very close, or the same thing as the physiological cross-sectional area. But in highly pennated muscles, this difference becomes significant. And I want to motivate the reason for why you might be wondering, well, if these muscle fibers are pulling this way, the only part of that muscle force will contribute to tendon motion in this direction, because, and this is like a vector-based argument, but if you have a force going off like this, only this component of it will actually be moving the tendon up, which is what this muscle is supposed to be doing. So this figure really nicely illustrates the benefits of having a pennate muscle versus a non-pennate muscle. Now, as we'll see, there's trade-offs, but first I want to highlight the benefits because maybe the detriment is more obvious. Notice how even though the anatomical cross-sectional area might be very similar between this muscle and between this muscle, the physiological cross-sectional area, if you imagine this is like a disc, that could be much bigger than this slice right here. So the idea is that by orienting muscle fibers at an angle, you can pack more of them in parallel in a given amount of space. Remember the way we're calculating this is each of these muscle fibers, or fibrils, I guess it would be, contributes some amount of force, and the more of those you can have stacked together in parallel, the more force you can produce. So that's the benefit to having a highly pennated muscle, is you can pack lots of individual myofibrils into a given area and produce a greater amount of maximum force. Now, there is a detriment. There's a downside to this. One of them I already talked about. One of the downsides is just that the force you produce, only this component of it actually goes towards moving the whole musculotendin unit. But there's a more subtle disadvantage to pennate muscles, and it has to do with the force length and force velocity curves. So maybe allow me to draw two of those down here. So let's start with the force length. Force length, and let's as a review, let's draw what we already know. So for your typical sarcomere, You have this very characteristic force length curve like this. Right here is this nice little window where those actin and myosin proteins are overlapping. We get maximum force production. I suppose that means that F naught for the maximum isometric force should be right here. The optimal length, of course, is the muscle fiber length where that happens. So let's say this is just your everyday typical muscle fiber. Now, what happens with a highly pennate muscle? Well, the fibers are going to be shorter. The optimal fiber length is going to be shorter, right? It's that versus that. And as a consequence, you see, number one, the whole curve shift to the left, and number two, maybe I'll just label this. Let's say fusiform. Fusiform, non-pennated. Because of the geometry of muscle pennation, what's going to happen to a pennate muscle is something like this. So more force, because more fibers, but the optimal length gets smaller, of course. But and this is the important part, the part to remember, the band of muscle lengths that you can operate in is smaller. So notice like this width where we could produce some reasonable amount of force. That's a much narrower band than, say, like this range here. So that's like a pennate muscle. There's a similar trade-off with regards to the force length, with regards to the force velocity behavior. And that looks like this. So again, let's just draw what we already know. So velocity, and we've got Vmax out here. Your typical everyday muscle, let's say it's a non-pennate muscle, would look like that, where that's F naught, that maximum isometric force production capability. And then if we wanted, we could draw the eccentric part out here if we wanted to. Now, what happens in a highly pennate muscle? Well, because the optimal fiber length for the pennate muscle is shorter, it turns out that the maximum shortening velocity is going to be lower as well. So in other words, the muscle cannot contract as fast. So that would be like Vmax for pennate muscle. So let's review the pros and cons of each. So maybe I'll write out pennate, non-pennate. So that's like this versus this. Pros for the pennate muscle. More force, right? Because we can pack more fibers into the same area. Also higher, and you see that here, right? Bigger isometric force. We could also just say like plus F naught. That would be a bigger number. Cons, though, we could maybe say force is not aligned with tendon. So that's right. This is not going the same way as this. I suppose it's not that easy to see. this force, oops, this is not going the same way as this tendon, which is, of course, what the muscle is supposed to be moving. Also, less, well, let's say narrower range of operation. That's how I would put it. Narrower and by range, I mean length. And also lower Vmax. Right? It cannot shorten as fast. And then I guess for the non-pennate, we could just say the pros and cons are exactly the opposite. All right, less force, but broader range of operation for its length and a higher maximum shortening velocity. One more thing to connect physiological cross-sectional area to muscle strength. In the last video, I introduced this idea of specific tension. And I said it was, I did not write that very clearly. Tension. And I said, maybe 30 to 60 newtons per square centimeter is a reasonable value. If you know the physiological cross-sectional area of a muscle, which you can get from, say, an MRI or an ultrasound or a cadaver experiment, I think one of the questions on the comprehension quiz from last week was from an ultrasound study where they were measuring what is this angle, what is the pennation angle, in order to calculate the physiological cross-sectional area of the muscle. Here's what you can do if you want to know what the maximum force production capability, the maximum isometric force produced by the muscle is. Let's write out max isometric force. Again, our abbreviation for that, F naught. This is the same F naught as this. That is going to be the physiological cross-sectional area of the muscle times this number. I think sometimes people use this like sigma as specific tension. Yeah, let's do that. Let's just call it a lowercase sigma for specific tension for now. But what that means is you get some physiological cross-sectional area, you multiply it by this amount of force per unit cross-sectional area of the muscle, and it tells you how much force the muscle can produce. And this relationship is remarkably accurate. And it shows you a few important things. Number one, the biggest factor for influencing muscle force is going to be the physiological cross-sectional area. Now, there's a little caveat to this, which is that maybe we should say, remember, this is maximum isometric force. So one thing that improves with training is your ability to actually recruit all of your muscle fibers together. So in some sense, this can go up even if this doesn't go up. This number is not going to change. This is something that's intrinsic to the behavior of muscle, and it's not only constant across people, well, roughly constant across people, it's actually roughly constant across species. So different, like humans and rats and rabbits and deer and dogs, this number is about in the same ballpark for everybody. So it's really that number, that physiological cross-sectional area, that influences the force production capability of muscle.